Here's a quick overview of delay-based processes. I've got a banging sound up here, and the looping region here. That should give us enough time to hear the delays. All right, so with a delay, 1,000 milliseconds or so, 1 second or so, it sounds independent. Could be another voice, especially if we found some other processes that could change the timbre. Time we shifting something in time, we're going to need to compare it to the original. And so we want this wet or dry mix here. The dry is the original. Wet is the fully processed sound that just happens later. Doesn't sound any different than that for now. So let's leave it in the middle so we can have a little bit of each. Okay, so if we get a delay period that's closer to, and we can follow along with these recipes here, about 1/4 of a second, 250 milliseconds, it starts to not sound so independent, but really more of it fuses with the sound and starts to become rhythmic, especially if we feed some of the output back into the input, say half of it. And so then we get a delay of a delay of a delay. If we want it to take longer to trail off, feed more of it back in. If we want it to trail off sooner, less feedback. Okay, so as our delay period gets even smaller, get distinct echoes so much anymore, but we start to get more of a lumpy reverb, and that starts to benefit from higher feedback amounts. See what I mean, lumpy reverb? Here we might want to tweak our wet-dry mix. Even smaller delay periods where we start to cross that threshold where between us hearing things in terms of rhythm, instead start to hear them in terms of pitch. And this is why I find it useful to call it the delay period and just the delay time. Sure, it's a measurement in time, but the period is the inverse of the frequency. And so if we were to do something at 10 milliseconds, we can fit 100 of those in 1 second. And so that has to do with the pitch that we hear now. This is called a comb filter effect. This is where we see that, you remember from the last unit, a filter is made by delaying samples just a little bit so that we can do our averaging or whatnot to reduce or emphasize changes, high frequencies, low frequencies, things in the middle. So filters are delays, and a delay also has filtering effects. Here we are with a comb filter. Even greater back amounts, 85 or so, 95%, really will turn anything into a robot. But speaking of automatons, let's see. We can also get some other effects down here. Did you notice some other things that we normally find in other areas of our menu? Happens when we start changing our delay parameters. Starts to get interesting effects. And so let's start with just, I'll put the feedback down at 0. And if I just steadily changed the delay time, and so let's see, let's switch to this fellow. And I'll have it steadily increasing the delay period. You'll see it here. And it's as if we're steadily traveling away from our source sound. And this is like the Doppler effect. This is what happens there. So if I really want to just hear the pitch shifted sound, I'll shift it all the way to wet and start. If I want to do it double speed, I decrease the delay period here. And set up here, we've got to set up a certain mixture of memory that we're going to store sound in. And so one plays the last 10 seconds at a accelerated rate. Let's see, we can also take hold of our sound here, and we just loop it. We won't hear it because we're only hearing the wet sound, but I could scrub freely and hear some of those effects of changing delay filters. We just had robot voices, and we're talking about changing. Why don't we make a robot, an automaton, change our values for us? And so That's where this word comes in, modulation. Modulation is a fancy word for changing. That's all. So we want to change it. Then we want to say, well, how fast do we want to change it, and by how much do we want to change it? That's our modulation rate and our modulation depth, respectively. And so for chorusing, let's set our delay period at just 5 milliseconds. Teeny tiny. That's in comb filter range, except we're going to leave our feedback at 0. And so we would just hear just a little bit of phase cancellation because we've got those two copies that are very close to each other. But if we heard that sound all by itself without anything changing, we might not tell the difference. It might just sound a little thin. And so let's see here. We'll go through here and we'll have this change the delay period at a very slow rate, in less than a full second here, 3/4 of a second to go up and down. Up and down by how much? Well, that's the depth. And so that'll be changing our delay period back and forth in milliseconds. And so let's get a depth of, I'll put it somewhere in the middle here. And remember, we've got one copy and the original. We're not going to hear any difference unless we hear both of them. Hear it a little thicker. Here's the original. And chorus. And you can play with these other parameters, but I'll leave that to you. What if we change it even more slightly? A modulation rate of something like 0.1 hertz, so it'll take 10 seconds to complete a cycle. We'll add in some feedback, and we'll have modulation depth. That's about fine. So I'll turn on my feedback to intensify the effect. This is flanging, as if we were pushing on the flange, that 90-degree flat surface on the edge of a tape reel, just to slow it down a little bit in relation to another copy of the same recording. It would slowly get out of sync, and then it would push on the other flange, on the other tape reel, and slow it down, let the other one speed up, and let them get back in sync. So you get that subtle sweeping up and down. How is that different from a sweeping all-pass filter? That'll be interesting to think about. Okay, well, that's all the delay base. Oh, wait, there's more! Because you can also use delays to make reverberation. We made lumpy reverberation before. Well, how would we make less lumpy reverberation? Look inside. What's inside here? Okay, there's some reading and writing to delays. All right, but that was the early part. There's early reflections that typically happen in reverberation off the nearby walls. So there's just a more simple delay effect. We can see there's only 4 of them in there, 4 taps of delays. But then we get to the do it. Whoa, you see all this? Okay, well, we had a lumpy reverb previously because we were only using one with a constant delay period. What we need to make it smooth is a mad mess of delay lines. And we need them to have delay times like these. What's the pattern here? There is no pattern. We're explicitly avoiding a pattern. Different delays that we're avoiding a harmonic series in this case. We've also got some low-pass filters in here because, well, what happens in nature is surfaces are likely to absorb the high frequencies faster than the low frequencies. And so this is a parameter called damping. Okay, so we can deal with the not the time of the individual delays, but the overall reverberation time measured in RT60. It's not meaningful to talk about when it falls to silence, so instead we talk about how many seconds it takes for the sound to fall by 60 decibels. There's our RT60 time. We can have a little bit of pre-delay, which is just a standard delay that happens before the rush of sound coming in. It's understandable to think that reverberation time suggests a big room, and kind of, but really reverberation time suggests a more reflective room. Harder surfaces that reflect, they would bounce a ball off better, they bounce sound off better. They might even bounce light off better. But it's pre-delay before the big rush of echoes come in, where we might still get some early reflections, individual echoes. It's pre-delay that makes a room sound big. Listen how far we are from the walls before it comes in. Here's our damping. This developer decided to give it to us in terms of percentage. And so with greater percentage, we'll have more damping, which means the higher frequencies will be absorbed more. Just like wet and dry and which side goes on which. It's arbitrary. It's up to the developer. And if nothing else, experiment. And so let's listen to our singer here in the Cherokee language. I'll let you play with that more. And damping here, let's listen to that. No damping means full spectrum. Keep all the brightness that we can. Higher damping. It's not like we're listening to the room through blankets, but that there's blankets elsewhere in the room that are absorbing the high frequencies gradually over time. And there's our delay-based effects.